Yes. Up and down, this and that, right?
Yeah, in a moment. Okay, yes.
So thank you very much for inviting me to my old institute, and in fact, alma mater. I've got, as Wodek mentioned, a PhD at physics in Warsaw a long time ago. And today I will tell you about ongoing work on primordial black holes. So ongoing work in which I am very heavily involved with a few other colleagues. How nice that your computer speaks Italiano. How good. Okay, that's the plan. And you, as you see, is 27 slides.
Just remove this part.
Great, thank you. I'm not sure whether I will be able to tell you all the material which is on this slide, and therefore I will start with the most important question-answer summary. So the question which I will address today is, do the primordial black holes exist in the dark matter halo of our galaxy? Is there any person in this room who doesn't know what primordial black holes mean or dark matter mean? So if not, then I would better explain right now.
I don't know.
Okay.
The dark matter, although I have some.
Okay. So okay. The question is, what is the dark matter? I'm answering quickly a question from the audience. What the dark matter is? Our galaxy rotates, and we astronomers, not you physicists, but we astronomers, measure rotation of the galaxy. And because the rotation is due to angular momentum of the stuff in the galaxy, stars, gas, clouds, etc., under its own gravity, Newton's physics is sufficient to calculate from the velocities of rotation the amount of mass which is needed to keep these orbits stable. And the big surprise, kind of new surprise, it is about 100 years old, is that there is far more mass in our galaxy than the mass that we see, okay? And nobody knows what this dark matter is.
Nobody knows. Because something is wrong. Nobody knows.
Yes. And of course, it is always like there is not much observation with theory, that there are only two possibilities. Either observations are wrong or theory is wrong. Okay? So consensus today is that observations are wrong, in the sense that we do not see all the matter in our galaxy, that this missing matter, this dark matter, exists really, but we don't know its nature. And the other answer, which is kind of far less popular among experts, is that theory is wrong. And the theory in this case is the Newton's theory of dynamics, not even gravity, namely that F equals A times m should be replaced by another formula, F equals A squared divided by A0 squared, which is a new constant of physics, times m. And that this other, everyone who would like to write anything, that is my book in Polish, okay? Please do write a line saying anything you like about my seminar or anything else. So F equals A squared over A0 times m. And this A0 is a new constant of physics. This formula, they say, works only for very small accelerations, okay? So small that you, physicists, never measure such small acceleration in your laboratories. We astronomers, however, do have to deal with this acceleration, these small accelerations, because these are typical gravity acceleration in the outer parts of the galaxy, okay? So there is absolutely nothing in physics which we can use to say, no, this formula is obviously wrong. It doesn't work. It may work. And the theory may be a correct explanation, a correct answer to the question, what is the dark matter? Namely, there is no dark matter, but we should modify fundamentally physics, which we are using today, okay? So if not for any other reason, for this one, the nature of dark matter, any question which is seriously connected with dark matter is interesting, not only for astronomers, but also fundamentally in physics. That's, we are talking about really foundations of the physics we have today. And the other link is primordial black holes. Stephen Hawking in 1974 suggested that a large part of this dark matter, possibly all of this dark matter, is in the form of small black holes, primordial black holes, which were originate right after Big Bang, because only at that time in the universe there were conditions to form such black holes. Later on, all these black holes which we astrophysicists know, stellar black holes which have masses of around 10 solar masses, or supermassive black holes which have masses of around from few millions to few billions of solar masses, are being produced by natural processes which we think we understand deeply even, and that there are no doubts that these more massive black holes do exist. But also we know that there are no today, in today's universe, processes able to produce small black holes. Because to produce small black holes, one needs to squeeze matter. And there are no such forces, such strong forces, which the forces are the smaller black hole, resulting black hole, the greater the force which is needed to squeeze it. And there are no such forces in nature able to squeeze matter to this sizes of primordial black holes, which therefore could only, as we think, be produced at the beginning of the universe, where the pressure density were much larger. than today. And my answer to the question, which I asked, do primordial black holes exist in the dark matter of in the halo of our galaxy? My answer is no. They do not exist. Jacku. And that is controversial. And some people are even saying arrogant astrophysicists answer to kind of a very beautiful idea, which many physicists, yes? Say it again, please.
Single or you say it's not the dark matter.
My dear colleague, if there would be a single primordial black hole in our universe, then we will never discover it. If there would be a single primordial black hole in our galaxy, we will never discover it. Yeah. So, yeah, so it is not, existence here is not in ontological sense, but in kind of a common sense, which we all share. That even if there is something which would look like a primordial black hole, but the number of these beasts is very small, then we will be never sure whether we discover them or not. So
I mean,
I will go into numbers in a moment. Okay.
Yeah, so you mean the dark matter cannot be in forms of primordial black hole?
Well, if you would like to know my private opinion, first of all, I don't believe that there is dark matter in our galaxy. Okay, I'm this small minority of physicists who think that Bekenstein-Milgrom theory, this modifying gravity Mont, is a correct answer to the question of dark matter. But that is not the subject of today's seminar. The subject of today's seminar is assume that dark matter exists in our galaxy. If it does, then is it possible to show that it consists of primordial black hole mostly, or is it possible to show the opposite? No. If there is dark matter, then certainly it is not in the form of primordial black hole. And to exactly this question, my answer is no. There are no primordial black holes in the dark matter in the halo of our galaxy. Okay, so I am. The number of this slide is 0, as you see. And I have 27 more to show. And I spent all my time on discussing this one. So my opinion is, yes, I know. I was studying mathematics at University of Wrocław. Very good mathematics at that time. Today also. And I remember that Andrzej Hulanicki, I know that you knew him. A very good mathematician. Oh, you knew Andrzej Hulanicki, no? Okay. But he died, of course, like most of the mathematicians some time ago. But on one of his first lectures of modern algebra, he proved to us that there is only one 0. If there is another 0, it must be equal to this 0 which exists. So that is somehow
contradiction.
No, it is the same 0.
Many 0.
Not many zeros. It's the same 0.
Maybe because 0.
And 0 times 0 is 0. So my claim and my colleagues is that in a few years, and this few years is not 20 years, but 5 rather than 20, we will know for sure from observations what is the answer to the question of a possible existence of this hypothetical primordial black holes in the dark matter halo of our galaxy. Definitely, that it will be no doubts. That's the claim. And this observation is microlensing, LIGO-Virgo-Kagra gravitational waves interferometers, and also, and this, of course, I assume that most of you, or probably all of you, know what microlensing is and what LIGO-Virgo is. But this other object, LMXRB, is low mass X-ray binaries. I will come to this, and that is something specifically astrophysical. Okay. So then, point by point, question. Are you going to ask a question?
No.
No, okay. So the new idea, which I'm presenting, how to check on primordial black holes in the dark matter halo of our galaxy, is based on a few steps. First, that if these hypothetical primordial black holes exist, they necessarily must collide with neutron stars in our galaxy. Okay? And then, when they collide with neutron stars, they necessarily, as a result of this collision, low mass black holes are produced. Low mass means that this resulting black hole have mass of around 1 solar masses. Such a light mass, low mass black hole cannot be produced in the stellar evolution. Black holes produced by ways which we astronomers understand are heavier than 1 solar mass. So if we observe black holes with masses 1 solar mass or slightly even lower, it would be a proxy for the existence of the primordial black holes, because there is no other ways to produce them. Nature knows no other ways to produce mass, sorry, black holes in this range of mass.
Oh, discovered.
Sorry?
Discovered.
That is, but look, they are low mass black holes, but these masses are far, far larger than these original primordial black holes, because original primordial black holes have masses in grams 10 to 16, 10 to 22 grams, where the mass of the sun is 10 to 33 grams. So there is some kind of 10 orders of magnitude and difference, and it is far easier to discover a black hole of with the mass of about solar mass than a black hole which is 10 to minus 13 solar mass. Okay, so that is the trick. That is why several of my colleagues think that this idea is kind of interesting, because it gives specific observational ways to be in check. Okay. because, and it is what I said, because this low mass black holes, in contrast to original primordial black holes, today, with today existing techniques may be observed, and there are some clues that so there are, as we astrophysicists call, candidates for such a few, but it is observable. There are no fundamental or reasons in physics or in technology which would forbid to observe such black holes. And the consensus is that if they exist, then they should be observed. So then we can reach them, observe them, or prove that despite all efforts, we haven't discovered anyone, and anyone means around 10, okay, practically. And therefore, if the number of candidates for such beasts in a galaxy using all these techniques will be less than about 10, then we may say primordial black holes do not exist. And that it would be fantastic, because this primordial black holes is the only reason I know of, and several of my colleagues know of, to seriously think of quantum gravity. Of course, there are people who are seriously thinking about quantum gravity, and they are not bothered by the fact that there are no experiments which could kind of support this thinking. If primordial black holes exist, then of course, it will be a very solid support for quantum gravity, because the origin of this primordial black holes is quantum fluctuations in the early universe. But I will be not talking about this. I will not talk at all about quantum gravity today. So, long time ago, in late 60s and early 70s, several good physicists suggested the existence of these primordial black holes. And it is till today an open question: do they exist? Not these physicists, but these primordial black holes or not. And of course, in this context, another link to quantum gravity should be mentioned, and that is Hawking radiation. Because Hawking radiation is directly relevant for primordial black hole questions for the following reason: that answering to the question in the paper which you gave me, this, and the question is, gravity on a large scale, does it necessarily look like it does on a small scale? I will not say what I think the answer to this question is, but this title stresses something which we relativists know, that unlikely in Newton's theory, in general relativity of Einstein, there is a scale, length scale connected with mass. You have a gravitating mass, and then you have a length scale, which is its gravitational radius. But if you have this length scale here, gravitational radius, Then, of course, there is a natural frequency, velocity of light divided by gravitational radius. And if you say that there are natural oscillations in gravity, whatever it means, okay? We are not going into details, but saying, okay, there are natural oscillations in gravity, and the frequency mass dependent frequency is given by this formula. Then you may say Planck formula and Boltzmann formula together it is kind of a distributed oscillations in equipartition, this kind of thing. Then you have a temperature, natural scale of temperature in gravity, which is given by this formula. It is really as simple as I'm showing. But if you have temperature, then you may say that you have a radiation because flux of radiation, black body radiation, is proportional to the force power of temperature. And you can calculate this flux or power. And that is exactly the Hawking formula for gravitational radiation. So the reason for Hawking's radiation is, in my intuition, coming from the fact that there is a natural scale in Einstein's theory. And if you connect this scale with quantum mechanics and statistical thermodynamics, you are getting immediately the Hawking formula for Hawking radiation. And so black holes Hawking radiate, and therefore they are losing mass because they are losing energy. And the question is, suppose that mass is m, how long it will take to radiate away all the mass? And the answer, which Hawking calculated, of course, himself in this 1974 paper, was that if the mass is 10 to 16 grams, then it is exactly the age of the universe needed to evaporate or radiate away the mass. So if there would be a black hole which originated at the beginning, close to the beginning of the universe, and its mass is less than 10 to 16 grams, it will evaporate till today all its mass. And therefore, if primordial black holes exist, and the existence fundamentally is connected with quantum gravity, and Hawking formula is valid, then there should not be primordial black holes in this dark matter halo with masses smaller than 10 to 16 grams. Okay, so that is why this Hawking radiation is relevant and important in the context. And I am showing here my colleagues, several of them already died. It's from Dennis Sharma, famous Cambridge team. They are in late 60s and early 70s. They were studying gravity, most classical gravity. And they discover all kinds of very fundamental facts, like Hawking-Penrose singularity theorems, etc. So your relativity group, if there is in this room somebody who has not read and studied this book, then he or she should. That's the best textbook on general relativity by Hawking and Ellis. and really fun to read in addition. So we don't know what is the typical of these primordial black holes. So from 10 to 15 grams to 10 to 36 grams. Let me remind you that Sun has 10 to 33 grams. So that is for small primordial black holes. They are not here for theoretical reason, and they are not there. And here is the fractional amount of the mass in the dark matter being in the form of the primordial black holes. So 10 to 0 is what Hawking thought himself, that all the dark matter mass is in the form of primordial black holes, and then kind of very tiny 10 to minus 6. And there were, and they are, observational techniques which astronomers use to eliminate a possibility that in a given mass range, such primordial black holes exist. And one of the most powerful is microlensing technique. Effect predicted by Albert Einstein in Prague in 1912. You have a distant star, and you aim your telescope towards this distant star. If there would be a chunk of matter which crosses the line of sight, this mass will bend light rays from the star and act like a lens. And therefore, during the flyby through the line of sight, the brightness of this distant star will go up for some time. And the light curve, so how the brightness depends on time, is characteristic. And from it, you or perhaps these people who are doing these microlensing techniques can learn several, not very many, but several important information about the lens. So massive program in which our colleagues from the Warsaw University Observatory were from the very beginning, and they are really leading expert on microlensing, Andrzej Udalski and his collaborators. But not only them, so there are a few other teams. They may say that in this mass range, starting from about 10 to 20 grams and larger, most probably there are no primordial black holes. And if they are, they must be here in this so-called asteroidal window. And asteroidal is that these masses are typical masses of asteroids in our solar system. Of course, it has nothing to do, the one thing. It is just that it is the same range of mass. Asteroids, moons, Mount Everest has the mass of 10 to 15 grams, or 10 to see, I don't remember, but it is just something large, but not like star or galaxy, but large on planetary or asteroidal scale. So we are looking for primordial black holes in this asteroidal mass range. And let me say, and rather make an excuse, this primordial black holes is not my cup of tea. I'm doing professionally in astrophysics totally different things. And I wrote only 3 papers on primordial black holes. One on 2009, because I had a very good assistant, Julia Becker, who is mentioned here, a German woman. He is now a professor, very distinguished already, a young professor at Bochum University in Germany. But at that time, as my assistant, she suggested that we may look for the consequences of collisions of these hypothetical primordial black holes with objects which we know exist in the galaxy, stars and planets. Okay? So we have done it. And the result was negative in the sense that we show that single collision is unobservable for fundamental reasons. Namely, we don't know what is the typical mass of primordial black hole, but we know very precisely what is the total mass of the dark matter in our galaxy, because it comes from this comparing rotational curve with the amount of mass which would produce this speed of this orbital speed at this distance, Kepler's law or Newton's gravity. So we know exactly what is the total mass of the dark matter. It is about 10 to 11 solar masses. Most of the mass of the galaxy is in the form of this dark matter. And if typically primordial black holes are small, then there is plenty of them, because this mass should be kind of divided to small pieces. Plenty of them, meaning that collision of this numerous primordial black holes with astrophysical objects will occur sufficiently frequently that we may have hope to observe them. But if they are in small pieces, then the energy released during a collision is small. The smaller the mass, the more frequent collisions are, but at the same time, the energy which eventually, of course, comes to our telescopes as photons is smaller. So there are 2 competing effects. On one hand, to observe a single collision, you would like to have primordial black hole masses to be very small. On the other hand, we would like them to have big masses. And these 2 demands contradict, cannot be met together. So our paper, which is kind of recognizes a good point in this community, says that said that no effect which one can observe due to a single collision of a primordial black hole with anything in our galaxy. Okay. But then perhaps I will skip the second paper and tell you that after a while, with different colleagues, I understood that single collision is unobservable for the reason which I explained. But if the collision is with a neutron star, this primordial black hole goes through neutron star, comes from the other side, but it is already bounded gravitation to neutron star. And it is because the energy dissipated is too small to be a source of observable for us photons, but sufficiently large to lower the kinetic energy of the primordial black hole motion to the level that it cannot escape to infinity from this neutron star. And then it will turn, hit second time, then third time, and then it will be captured by neutron star. Once it's captured by neutron star, it accretes the matter of neutron star, growing itself in its mass and causing at the end necessarily gravitational collapse. Okay, and this gravitational collapse, of course, can be observed because the energy release is mc square, and m is the mass of the sun. This typical supernova explosion and a power, typical supernova explosion power. This can be observed, but that is even not our point. Our point is that this way, through this final collapse, a light mass black hole will be produced. And these are, guys, this is what we are looking for. We are looking for the product of this complicated interaction between primordial black holes with neutron stars in our galaxy. And so that is quickly what one must study theoretically in order to describe the process. I will not go through it, but make a summary and reminder of this point. In collisions of primordial black holes with neutron stars, low mass black holes are formed. That is what we are saying. And that is through the line of calculations and argument. Let me stress, not one, but nature cannot avoid this. If there are primordial black holes, they will collide with neutron stars and will produce these low mass black holes. No escape. And we today, we astronomers, have techniques to detect if they exist, these low mass black holes. So the first thing is, of course, to study the interaction between these two species, primordial black holes, populations of primordial black holes, and population of neutron stars in our galaxy. And of course, there are standard techniques to do this. They all come from really kinetic theory of gases, that you have two gases, particles, the cross sections, all these kind of standard things. So we have done it. I would not say the best way one can do it, but the only way one can and should do it. And the results are interesting in the sense that if the masses of these primordial black holes are small. So they are just slightly more than this 10 to 16, which is the lowest mass due to Hawking radiation. Then all neutron stars in our galaxy, and it is about 10 to 8 neutron stars in our galaxy, should be turned into this low mass black hole. So you see that there is this, that is the number of low mass black holes, depending on the fraction of primordial black holes of the total mass of the dark matter and the mass. So for small, even if the fraction is 1%, all the neutron stars will be killed. Okay. So it is obvious that there is a hope that from these statistics, observing candidates for these low mass black holes, we may say something solid and interesting about the existence of the primordial black holes. And then I am here explaining with some details about different theoretical issues which one must address in studying this process of collision, flyby of a black hole through neutron star, final collapse, etc. And that is really interesting. And there is a lot of physics, also fundamental physics involved. But let me tell you that neutron star radius typically is 10 kilometers. Black hole, which has a mass of 10 to 20 grams, has its Schwarzschild radius of 10 to 8 centimeters. So when such a small black hole goes through neutron star, it directly interacts with matter in this cylinder, okay? 10 kilometers across and 10 to minus 8 centimeters in radius. Neutron stars have densities of 10 to 14, 10 to 15 grams per cubic centimeter. So one can easily calculate that there is 10 to 4 gram matter in this cylinder. But the black hole has 10 to 20 grams. So it's obvious that the matter, the fact that there is matter at all nearby the trajectory of the black holes through neutron star is totally irrelevant. And in fact, the exchange of momentum between black hole and neutron star is due to gravity, because being very small, it has a serious mass. And therefore, it will attract matter inside neutron star. This matter will start to move and collide with itself, dissipate, etc. So that is an interesting per se process, which was studied, of course, in different contexts, because it's a kind of a typical situation in astrophysics that, for example, a star is going through a cloud of stars, okay? So not interacting directly with individual stars, but attracting them, and momentum exchanges through gravity, and it is called dynamical friction. There is a kind of a serious knowledge about this. to which we also contributed something which perhaps is not I would say it's cute, because one of my collaborator, Iży Chorak, a young professor at Charles University, and Axel Brandenburg, deputy director of Nordita in Stockholm, and Kirylo Bondarenko, who is a Ukrainian postdoc at Nordita in Stockholm, studied this dynamical friction with a kind of a new approach, fresh eye, and we calculated oscillations of stars in fundamental mode, which will be excited. If you like this kind of things, it is because you will immediately come into second order Bessel function and things like this. So we know how energy is being dissipated when black hole goes through neutron star. As we calculated this analytically, and we simulated this numerically, and there are no doubts about this. And in this cartoon, I am showing how does it look. Namely, that is the gravitational, in Newton's theory, potential of a neutron star. Neutron star surface is here. Black hole comes from energy close to zero because it comes from infinity, okay? And in Newton's theory, then energy is zero. It strikes neutron star, energy goes down, black hole appears on the other side of neutron star, here hits the potential barrier, turns back, with the same energy hits for the second time, and then it ends up in the center of neutron star. I am hard of hearing, so I will come closer and ask you.
The unique velocity of this black hole, which appears, yeah, if it's very fast, it goes through and
No, it is not like this. It is because, of course, in a general case, not connected with this specific situation which we are talking about, namely dark matter. We know what are the velocities of these hypothetical dark matter particles, whatever they are, precisely. So we know that in say around sun, this velocities, typical velocities of objects in our galaxy are around 200 kilometers per second, okay? But the escape velocity from a neutron star is about 1/3 of the light speed. So the fact that they are is irrelevant. It is they would be kind of motionless, and it would be the same thing. So, but of course, I admit your point is correct, but kind of in principle. But in practice, if you take these numbers, then the initial energy is zero. It comes from infinity with zero velocity. And then when this little black hole is at the center of a neutron star, it of course accretes material of neutron star. And Hermann Bondi was the first one who studied spherical accretion in great details, and there are Bondi formulae which are describing this analytically, but matter in a neutron star is very complicated. Some of them is in the crystal form, some of them is degenerate gas. So one must, and also radiation will be produced, and this radiation will kind of slow down the accretion. So astrophysically, it is what physicists sometimes call dirty astrophysics. So here, there are fundamental reasons analytically found by Hermann Bondi, which give us typical timescales, and then extremely detailed, boring astrophysical calculations describing realistically through supercomputer simulations this process, and they fortunately agree. So because I don't know how it goes in physics, but in astrophysics, we still believe in analytic results, okay? If we have results of some supercomputer simulations and there is no analytic models which would explain fundamentally the results, we think that perhaps numerics is not yet a part of physics, but it is informatics or something. So excellent understanding, agreement. There are no doubts that it will go. I mean, of course, it may be that our theories are wrong, but based on what we know about physics of dense matter today, there are no doubts that it will be like we calculated. This process of Bondi accretion is extremely fast. It goes like hundreds to thousands of years, and most of the matter from the neutron star will be in this initial central primordial black hole. And this we calculated. And then the final collapse. This has not yet been studied in such great details as this Bondi accretion, but there is no fundamental reason to think that there would be no final collapse. Oppenheimer and Snyder. This photo is from the movie, which probably all of you have seen. And the scene itself is that Snyder, who was a student of Oppenheimer, runs into the room shouting, "Our paper was published, our paper." A beautiful moment in the movie. It was not only published, but it was published in Physical Review Letters, okay? The first paper of Snyder. And this paper is one of the, in my view, one of the most important papers in Einstein general relativity theory, because it proved formation of black holes, and in particular formation of the event horizon. Beautiful paper. And it is connected, this paper, to you at physics in Warsaw. Namely, Infeld, Leopold Infeld, had this custom of giving old papers to doctorants, saying, in Polish. Panie Lasota, niech pan to zreferuje, for example. And Infeld gave Oppenheimer-Snyder paper to Jean-Pierre, asking to present it on one of these very, very important seminars at Chorza at Infeld's time. And Infeld was totally convinced that it is a nonsense, because like Albert Einstein himself, Infeld did not believe in the existence of black holes horizons. Einstein wrote even a few papers on this, saying that black holes is total nonsense. But Jean-Pierre studied this paper, which is beautiful. It's really nice to go to this old literature and to read it. And said to Infeld, Panie profesorze, but they are right. And they are right. Black holes are formed during gravitational collapse. But of course, Oppenheimer-Snyder was particles, no pressure, zero pressure. But in neutron stars, situation is far from this situation. So it is more complicated. We are doing this. We have no doubts that there would be final result, this collapse, it must go. And then I several times said, producing of these low mass black holes, the only process which we know of to produce such a low mass black holes, low means around 1 solar mass, is through these collisions of primordial black holes with neutron stars. But that is kind of not exactly true, because of course there are some models, possibilities, like boson stars, gravas. I will not go into details. Excellent review of exotic objects which kind of mimic black holes by Victor Cardozo, who is the #1 in this kind of subject in living reviews in relativity. Really very good. It is a few years old, but really is still, if any of you would like to read about exotic objects like wormholes, grava stars, that is the place to go. Okay, and we accept that there are other ways, but what we are saying is that from our calculations, we are giving the lower limit for the number of these beasts. So if the number real observed number will still be lower, then of course the fact that there are other ways of producing them makes the thing even worse. So if there is not enough low mass black holes in the dark halo of our galaxy, it means that primordial black holes do not exist, really. And the fact that they may be produced some other ways than the way described by us obviously makes things even. So this I said. And now I have few slides which describe the status of observations today. Okay, and I do see that I am running. I'm sorry for that. Over time. So let me say that in all these observational techniques which are being used and will be used to study the existence, possible existence of these low mass black holes, results are kind of, as today, not certain, because in microlensing, in LIGO-Virgo-Kagra, and in these low mass X-ray binaries, there are few, and few is less than 10 candidates for these guys. So the question whether it's already proved that these low mass black holes do not exist in our galaxy or not, cannot be answered because we must wait to improvements of all these techniques, in particular improvements of LIGO. This LIGO-Virgo-Kagra, and other people are joining them, team, are very well known and impressive. And that is why I'm convinced that in a small few years, we will know for sure whether these proxies for primordial black holes exist in our galaxy or not. Still few more slides, but I think that I told you the message. So let me make a short summary. Consensus is that dark matter really exists in our galaxy. Then hypothesis, originally by Hawking, is that most of this mass is in the form of primordial black holes. Neither dark matter nor primordial black holes have ever been observed directly by any technique. So we don't know whether these things exist or not. However, if primordial black holes exist and they are substantial, and substantial means more than 1% fraction of the dark matter, the already existing techniques may pick up these proxies for primordial black holes in a small few next years. So I'm convinced that the answer will be no. There are no primordial black holes. And if there are no primordial black holes, then I think it will be a problem for quantum gravity people, because all this, especially if they are involved in early universe cosmology, they are absolutely convinced that from fundamental physics, which they are touching, not yet through quantum gravity, but the models they have, primordial black holes must be formed. So that is all which I said you today about primordial black hole question. Thank you. I will sit down.
Why are you convinced that primordial black holes do not exist? Why?
My dear colleague, we are convinced about things from ideological reasons, always, okay? If we know or we doesn't know, it is because we are physicists. But if we are convinced, I think that they do not exist. First of all, because the dark matter is an illusion, and we should modify Newtonian and, of course, Einstein dynamics the way Mordechai Milgrom and Jakob Bekenstein are telling us we should. So that is the reason. But of course, there is a very serious, as you all know in this room, criticism of Milgrom-Bekenstein hypothesis. There are people who would not even call it theory because there are no fundamental reasons for this universal acceleration. But to me, it is a big mistake of the community because the situation is like this. Distance from the center of the galaxy and measured accurately rotation of the stuff in the galaxy. Location of the sun is here, and this looks like this. So there is flat curve, while from Newton's theory and from the amount of matter which we do see, of course, the curve should be Keplerian curve. And it should be like this, that very far away from a gravitating mass, orbital velocities are smaller and smaller. So that is the reason, this huge difference between theory and observations, that people believe in the dark matter existence as some material substance. Okay, and in our galaxy, it is, as I mentioned, about 200 kilometers per second, this flat part of the curve. But in different galaxies, these curves look differently, and the saturation is at different level of velocity. Now the thing is that this Milgrom formula with one additional fundamental constant to physics explain all these curves, hundreds of them. And really, these colleagues of mine who are in this business, and when we, this small minority, Milgrom, Bekenstein, are telling, but hundreds of curves are fitted just by one additional constant. By chance, it's meaningless. So that is why I really, the reason why I think that there are no primordial black holes, because I think there is no dark matter. And the reason that I think there is no dark matter is that with one constant, one is explaining all rotational curves. Of course, there are problems with explanation of other effects. Sorry?
What about this A?
I'm not sure whether I understand your question.
So in what way your modified Newton's law gives in some limit the usual Newton's law?
No, it does not. It is that this formula is valid only when acceleration So there are kind of two regimes. Small accelerations are described by Milgram's formula, but kind of larger accelerations are explained by Newton's formula.
So
And let me add, that this A0 is such a small acceleration that we are not experimenting with this kind of small acceleration in our laboratories. So there is no direct experimental knowledge of how bodies behave. What is dynamics of bodies? Because it is not gravity, it's whatever.
but it's counterintuitional. Usually quadratic terms are relevant when something is bigger. On the other hand, when something is small, then linear terms are.
Yes, that's right. That is why so many people.
And here this quadratic term dominates.
Yes, I fully agree. We don't. Nobody, including Milgram and Bekenstein, who died, of course, a few years ago, are saying that they have some fundamental physical reasons for this behavior. It is just like Niels Bohr model for hydrogen atom, and especially the location of spectral lines, okay? Formula, which came out of the blue. No, at the beginning, nobody could explain it, but was perfect, was explaining all series of lines in the spectrum of hydrogen atom. So, of course, I agree with the critics who are saying, till we have some real serious fundamental theory, we may say it is by chance. But nevertheless, I don't think it is by chance. And ideology, it is not physics, it is my ideological background. I believe no dark matter and therefore no primordial black holes.
So I'm afraid we don't have more time for discussion. Our time is over, so let us thank the speaker again. Thank you.